Good morning, my YouTube viewers. It's Crystal here. I'm just here this morning because what I wanted to do is I wanted to do a code review. And what I've done is I made a neural network, a regression neural network using JAX on the Boston house prices data set. And what I wanted to do is I wanted to go over that with you. And I think in my last code review that I did a code review in NumPy. Well, the code in JAX is similar to the code in NumPy, but there are a few changes. And the reason why is because the random numbers in JAX are different from the random numbers in NumPy. That's number one. And then number two, NumPy arrays in JAX are immutable, which means they can't be changed. And because of that, you have to use different programming techniques to actually be able to change that. So I've written a program in Google Colab, and Google Colab is a free online Jupyter notebook, and it's a great program to use because I was experimenting with another compiler editor, which was VS Code, and I didn't like VS Code nearly as much as I liked Google Colab, so I even uninstalled VS Code from my computer. And another thing that you can do while I'm on the subject is you can use the Python's IDE, but the only thing about the Python's IDE is you have to be able to install the other libraries into your computer to get it to work properly, because the only thing that the Python IDE will work on is actually Python, and Python does have a number of modules in it, so if those modules are in it, then you can use it. So I've not actually installed any libraries on my computer. I just use Google Colab. But also wanted to say, while I'm on the subject, there's a new version of Python out. It's 3.12, and it's got a lot of changes and deprecations and removals. So I did actually do a blog post on this telling you what's been changed or what's been deprecated, but it's a lot of changes to this version of Python, so you might want to look at that as well. So now that I've talked about all the new things coming up with Python programming language, what I'll do is I'll commence with the code review. And the thing I would like to say again is Google Colab does not have an undo function, and because Google Colab does not have an undo function, if you accidentally overwrite or delete any code, then it's going to be problematic. But you might be able to go into the save changes, and you might be able to retrieve the code back from the same save changes, but it's not actually a guarantee. Okay, so just keep that in mind. I'll show you. So here's your save changes. And so, like, if you wanted to go back and get some code, you could look through the save changes and see if you can find the code through the save changes. And I found that quite by accident a while ago, whenever I had accidentally overwritten some code. So now what we'll do, now that you know all this neat stuff about Python and Google Colab, once we've created our Jupyter notebook, then what we want to do is we want to import our libraries. And since we're using JAX, we're going to import JAX. That's going to create your neural network. We're going to import pandas. That's going to create your data frame. We're going to import sklearn. That's going to provide your machine learning functionality. We're going to import seaborn, which provides your visualization with a statistical slant to it. And we're going to import matplotlib.pyplot as PLT, and that's going to give you visualization as well. Okay, we have to load the CSV file up, and what has happened is sklearn no longer maintains Boston house prices. And what I would like sklearn to do is maybe put another house price data set in its place, such as California house prices. But they no longer use Boston house prices because I had a bit of a racist slant to it, and because it talked about black people, and it also talked about underdeveloped, like, so the B is for the black people, and there was another one about like disadvantaged people or lower class people or something like that. So there were two columns that were a bit, some people would consider them offensive. But this data set came out, I believe, in the 1980s. So at that point in time, it was more accepted, whereas it's not accepted now because we're all woke now. And so you can't, it's hard to get that data set. So it's no longer on sklearn. But I do think that sklearn should replace it with something like California house prices or something like that. You know, they shouldn't just take it away and then not give another house price in its data set in its place. And then after we've loaded the data set, I use Jason Brownlee's data set. We're going to define our columns. So you've got, so the header equals none, and then we define the columns so you can see what the columns are. And then we're going to define our X and our Y variables. So X is all of the columns except for the last one, and that's your dependent variable. Sorry, that's your independent variable. And Y is the last column, and that's your dependent variable. And then what we're going to do is we're going to convert the X and Y variables to Jack's arrays. And then we're going to use sklearn standard scalar to standardize the data. So we've standardized the data here. Now after we have done that, we're going to use Seaborn to analyze the target. We're going to create a histogram, and so you can see this is what the target looks like. It's a regression model, and so you can see that there are a few outliers out there as well. After we have analyzed the target, then what we're going to do is we're going to split the data set into training and testing sets, and we're going to use sklearn to do that, train test split function. And then after we've done that, we're going to define the neural network. Now the difference between a regression neural network and a classification neural network is the regression neural network doesn't have an activation function in the output node. And then because it doesn't have an activation function in the output node, then the information or the data just flows from the input to the hidden to the output. Because in a neural network you have input nodes, hidden nodes, and output nodes. And then normally you have an activation function at the output node, whereas you don't have that in a regression. So in a regression, it's really just like linear regression, really. And maybe that's why most people don't make regression neural networks. So the input size is the number of columns in the train shape. And the hidden size is 64. They just made it 64. But we could have done 128, or you could have done another one. And the output size is 1 because it's going to be a regression. And now we're going to initialize the weights and biases for the hidden layer and the output layer. So we have to set our random number. So key is your random number, which is 42. Hidden weights equals jax.random.normal. Key, and then the shape is the hidden size, input size, and your hidden size. Hidden bias is jmp.zeros, hidden size. Output weights equals jax.random.normal. Key, and then shape is hidden size, output size. And output bias equals jmp zeros, output size. So what we're going to do is we're going to look at what are weights and biases in a neural network. What are weights and biases in a neural network? It says weights set the standards for the neuron signal strength. This value will determine the influence input data has on the output product. Biases give extra characteristics with a value of 1 that the neural network did not previously have. The neural network that needs extra information to efficiently propagate forward. So that's your weights and biases. Okay. So now you know a little bit about weights and biases, and that's what we've initialized in the definition of the neural network. And then what we're going to do is we're going to train the neural network. So the learning rate equals 0.001 and number of epochs equals 5,000. So we're going to set up a fourth loop that's going to iterate through the number of epochs. So because it's 5,000, it's going to iterate 5,000 times. But it's going to go 5,000 times for every row in the data set. So you're going to set up your forward propagation. Let me just take these out. So we're going to come over here and we're going to say I'm going to find out about forward propagation and back propagation. Back propagation is the process of moving from right output layer to left input layer. Forward propagation is the way data moves from left input layer to output layer. But what the back propagation does is that helps with the error. Okay. See what it says here. This is back propagation. Back propagation is a process involved in training a neural network. It involves taking the error rate of a forward propagation and feeding this loss backward through the neural network layers to fine-tune the weights. Back propagation is the essence of neural net training. So that's your back propagation. It goes from the output layer to the input layer, and it takes the error rate to the forward propagation and feeding this backward through the neural network layers of it to fine-tune the weight. So that's what it's doing. It's fine-tuning the weight. And see what we've got here. Forward propagation is where input data is fed through a network in a forward direction to generate an output. The data is accepted by hidden layers and processed as per the activation function and moves to the successive layer. So that's your forward propagation and your back propagation. So we set up the forward propagation where it moves through the from the input layer to the hidden layer to the output layer, and then what we do is we compute the loss and we make predictions in the forward propagation, and then the predictions is the loss is predictions minus the actual y-train value. Then after we've computed the loss, then we have the back propagation. So the back propagation fine-tunes your weights and bias. And then we update the weights and biases continually throughout the for loop. And then we print each epoch if it's divisible by 100. So we've got 5,000 epochs, and then so you've got your loss at 5,000 epochs of 10.5621. And then after we have trained the training data into the neural network, then we're going to evaluate the neural network with the test data. So we're going to hidden layer input equals JNP dot X test hidden weights plus bias. So we're going to be using the dot product of X test and hidden weights. So let's see what dot product is. The dot product is a way to multiply two equal length vectors together. Conceptually, it is the sum of the products of the corresponding elements in the two vectors. So the vectors have to be two equal lengths in order to do it. So that's your dot product. You've got your hidden layer input, which is a dot product of X test hidden weights plus hidden bias. You've got your hidden layer output, and which 1 over 1 plus JMP dot EXP minus hidden layer input. You've got your predicted prices, which is JNP dot of the hidden layer output and the output weights plus the output bias. And then I decided to print the predicted prices because I wanted to see what it looked like. And then we're going to calculate the mean squared error of the test set. So test loss equals JNP dot mean predicted prices minus y test reshape -1, 1, and it's squared. So we print the test loss. The test loss is 14. And then what I wanted was the mean squared error, because root mean squared error, really, because that's how I personally judge things. Is MSE equals JNP dot square, brackets JNP dot subtract, brackets y test, predicted prices, brackets dot mean. And then RMSC is the square root of MSC, and then we print root mean squared error, and it's 11.33. We use Matplotlib to visualize the true values as they are overlaid on the curve, so you can see that. And then we're going to compare this to sklearn, because sklearn has a neural network as well. So we compare it to sklearn, and it says it's 3.78, and then the what are we going to say, the illustration is very similar to what it looks like. But on SK Learns, we had 5,000 iterations, and we had 5,000 iterations on the Made from Scratch neural network. So it's using pretty much the same parameters. But what I wanted to do here is just to spice it up a little bit. I don't think I hope I'm going to get this right. Hope I got it right. COIF core. See what we're going to look at. NumPy. Core COIF. Because I didn't want to try to run it and have it be wrong. It's core COIF, not COIF core. So we're going to run it again to have a heat map, because I didn't put a heat map in it to begin with. And the thing is that the documentation on JAX, in my opinion, is not as good as the documentation on NumPy. And since, well, that doesn't work. And since the JAX is similar to NumPy and similar to NumPy's API, and the way that it was written, quite often I go into NumPy to look it up. So we've got our, and you'll see that's how, see, if it's a NumPy array, then the core function doesn't work. So you have to use core COIF xt, and then you've got to transform the matrix. So that looks good. Still got a root mean squared error of 11, and then on SK Learns you have a root mean squared error of 3 point something. So the 3.78. So the root mean square error on sklearn is better than the root mean squared error on the homemade neural network. And what I would like to say is that I had found a neural network that had gradients and VMAP and JIT on it, and I thought, oh, well, this is a better neural network to use. And so I tried that out on the Boston house prices, and the root mean squared error was a lot higher. And not only that, we'll just say that it didn't look very good on the illustration when you plotted it on a graph. And I tried it on Kaggle because I was working on a Kaggle competition question, and it crashed the system. So JAX is, it's a great library. That's what I've been using for about the past month to try to learn JAX and learn how to do all these things in JAX. But a lot of it's more sophisticated functions when they don't work that well as far as I can see, and they crashed Kaggle. It didn't crash my system, and so I'm not even going to do a code review on this this code where they use VMAP and JIT and GRAD, because it didn't work out as well. The accuracy was not as good as just a standard NumPy-like code. So I'm on 25 minutes, so I've been talking long enough about JAX and about neural networks and about predicting on the Boston house prices with JAX. So I'm going to go ahead and conclude this video. So I would like to thank all of my subscribers for supporting my channel. If you like my channel, please like, subscribe, and share. If you want to be notified whenever I make a new video, please tap onto the bell button next to the subscribe button. And thank you very much for supporting me and my channel and watching my video.